still not fully integrated somehow, because in the program it's a bit different, and also due to security reasons, it's kind of difficult to have really full installation. So the first talk, first installation, Gannett Poses, is presented by Hamid Ekbalzadeh. Great,
all right.
Thanks.
Hello, everyone. I'm Hamid from the Department of Computational Perception at the Johannes Kepler University of Linz in Austria, and I'm presenting Gans and Poses, an interactive generative music installation controlled by dance moves. Let's watch a demo video together. Gans and Poses is a musical game, and the game controller is your body. The yellow stars you see in the corner of the screen represents the scores or the points you collect through the game. And to collect more points, you have to dance. The green bar that you see shows that you passed the current level. And the red bar that you see here means that you didn't pass the level and you're running out of time, so you have to dance harder. And of course, if you dance with other people, you progress faster. So you can dance with the others, and it's better if you bring your friends. The more you progress through the game, the more complex the patterns of the music become. So it's a real-time music generation, and the music that is generated in real time reacts to your dance moves. And every time it's dynamic and changing all the time. All right, so let's see how it works. We use a deep neural network for pose estimation. We receive the images from the webcam, and we estimate the posture of your body. And these postures then are sent to our dance recognition system, which is a recurrent neural network that detects your dance moves. We trained our dance recognition system on the dance moves we collected from a video game called Fortnite. We use a real-time music generation algorithm that generates musical patterns with different levels of complexity and loudness. And our generation algorithm is a generative adversarial network. And to learn to generate musical patterns, it has to compete with the discriminator network that can distinguish between generated patterns and real patterns from professional musicians. And to win this game, our generator has to generate music as the professional musicians. So this way, it learns to generate realistic musical patterns. Next, we send all of this information to our game engine that in return creates visual feedback that is shown on the screen that you kind of learn what's going on in the game. So you will get some visual and text clues about the progress and the state in the game. And in the end, since we generate MIDI music, we synthesize the audios using Ableton Live. So, thank you for your attention. Please come and visit our installation and put the headphones on and show us what you got. Thank you.
Thank you. The next presentation is by Bob Sturm.
Good morning. My name is Bob Sturm. I'm here to promote two websites that we've created under a project funded by the United Kingdom Arts and Humanities Research Council, folkrn.org and the machinefolksession.org. These work in tandem together, and my colleagues Matthew Toby Harris and Oded Bental have also been involved. So this is a deep LSTM, or long short-term memory network, that's been trained on over 23,000 music transcriptions of primarily Irish and English dance music. And it's got 3 hidden layers. You got 5.6 million parameters, and it works pretty well. So folkarnin.org is the first website. This is where you can yourself explore some of these models. You can change some of the parameters here for the model, and you see the output up here. It's a textual representation called ABC notation, and that is rendered in staff notation, which you see below. You can hear it, and if you like what you have produced, or you want to change it, you can also input some different starting tokens. If you like what you hear, you can then submit it for inclusion into the machinefolksession.org. Now, this is a repository of hand-selected tunes that are generated by or with the machine. It could be folkarnin, or it could be another machine. And we're collecting these tunes, these transcriptions here, for posterity and for promoting the machine folk music genre. And here you can see some videos that have been submitted. So Shimon the robot, produced by Georgia Tech, plays one of the folkarnin tunes. We have a tune of the month. Each month, the users of the website vote on one of 4 tunes, and that tune becomes material to practice, and if you're so brave, to record yourself and upload to the website of you playing the tune. So far, we've had one in September, and then this month we have a tune of the month. If you attend the banquets, a group of us will be playing the tune of the month for this month, the Silver Keyboard. We also had a folkarnin composition competition where we invited composers to interact with the application and to create their own composition. It could follow very closely what the computer generated, or it could follow it not so closely and use it as inspiration. And the winning piece is by a Welsh composer, Derry Lewis, and that will be performed at the O'Reilly Artificial Concerts on October 9th in London. So if you're there, go attend the music. And there's going to be several other pieces generated by the computer, some of which are going to be played on the organ, composed by folkarnin, and then orchestrated or arranged in a chorale format by Deep Bach, by Gaetan Hadyaris. So 2 machines were involved in that, and finally a human organist. And finally, we have, for the past 6 months, an album of folk music has been in circulation for reviewers and listeners to comment on. The story is that a family in Ireland were paying tribute to their deceased grandfather and recorded this album. And in fact, the album, most of it was generated by, material was generated by folkarnin.org. And the reveal has happened now since Monday. You could go to the SoundCloud website of the O'Connell family and friends, or you can search "Let's Have Another Gun on 'Em" and listen to the music. And the reviews have been very positive. One of the reviewers who's played it on the radio has said this is pure drop, which means you can't get any more traditional than this. And when we gave the reviewers a chance to respond and to opt out of the study and anonymize their responses. But so far, the responses have been very positive. Some have said that they're sorry that the backstory isn't true, but that the music on the album really speaks for itself. The musicians are fantastic. So that's been a very fun experiment. So have a listen yourself. And come by the stand and generate a folk tune. Thank you very much.
Thank you. So the next presentation is called Jam Sketch, presented by Tetsuho Kitehara.
Good morning, everyone. So here, we'd like to introduce Jam Sketch, which is a system that enables you to play improvisation only by drawing melodic outline. That is a curve that represents the overall shape of melody, like oops, what? Like this blue line. Okay, So, you know, our goal is to enable non-musicians to play improvisation. So to achieve this goal, so we have to consider two issues. One is a human interface. Okay, so traditional musical keyboards are too difficult for our target users. So more intuitive, easier, and no musicians-friendly human interface should be developed. The other is automatic music generation. So, our target user is non-musicians. So, input data given by such users should maybe musically incomplete or abstract or musically incorrect. So, from such data, so the system needs to generate musically appropriate melodies. So to resolve the first issue, so we adopt melodic outlines as an input. Okay, so once you draw a melodic outlines on your fingers or a pen or mouse, so the system immediately generates melodies according to the melodic outlines you draw. So for the second issue, so we developed a melody generation algorithm, so based on a genetic algorithm. Okay? So for melodic outlines given by the user, the system calculates a fitness function that involves the closeness to the outline and n-gram probability and so on. So by calculating this fitness function, so the system tried to find melodies that satisfies both the closeness to the outline you draw and musical appropriateness. So here, we developed new functions. So one is interactive seed adaptation. So if you like the generated melodies, please press the great or good button. Then the system saves these melodies and uses them for the next melody generation. The other is parameter adjustment. So you can control parameters like these four parameters using a MIDI mixer. So user can make variations in melody generation by controlling such parameters. Please come to my demo booth and enjoy improvisation. Thank you very much.
Thank you. Okay, last presentation by Hugo Scurto riding the Co-Explorers.
So hi everyone, thanks for coming to this morning session on interactive machine learning. So my name is Hugo Scurto, and I'm presenting an exhibition, an installation that we conceived specially for ISMIR conference, which is called Riding the Co-Explorers. So this is an installation based on work done on the Co-Explorer part, and the riding part is added for ISMIR part. So I'm just going to talk a bit about the Co-Explorer part. So the study all begins with this finding. So we observed the mainstream tool for sound design, and we observed that they mostly present users with high-dimensional parametric interfaces. So I took an example. Maybe the creators of this plugin are in the room, I don't know, but anyway. So this is a VST, so this is mostly used for synthesis. So you have a lot of synthesis parameters, of course, or also audio effects. So this kind of human-computer interface are, of course, very good and efficient for a lot of sound design tasks. But they may not be the best to explore a great variety of sounds because of the exponential number of parameter combinations. So our interests. So instead of having only the user kind of exploring the sound space given by the parameters, we wondered what if the machine could would automatically explore the parameters, so in parallel to the user, while learning users' preferences towards the parameters. So we began thinking about this kind of new paradigm that we called co-exploration, where a user actively explores the space of possible ideas that he may have, and the machine will learn incrementally a way to explore so that it pleases the user. So it's kind of different from the recommender system approaches, because here we don't have any hypothesis on the consistency of the user, because he or she is maybe exploring. So of course, what algorithm will suit such autonomous parameter space exploration and interactive user learning? So we decided to focus on reinforcement learning, but on an interactive reinforcement learning paradigm. So it is a bit different from reinforcement learning. This time you have a user that gives feedback to the machine interactively. So in blue you can see a kind of artificial agent who would take actions on the parameters of the VST, which in turn will generate sound, and the user would tell the machine if it's good or bad. So as this parameter space of the VST may be very big and the user may not be consistent, we investigated recent advances in deep interactive reinforcement learning. So we can talk later about it. It's a recent paper published in the Artificial Intelligence Conference, which is adapted to such a setup in high-dimensional spaces. So one main aspect of our work, we wanted to focus on what interactive features should be added to build a mainstream sound design tool that may suit professional users' need, because probably users wouldn't want to give just I like or I don't like interactive setup. So this we ended up with this system that we called Co-Explorer. On the up left, you can see the user feedback still, so telling the machine if it's good or bad. And we added other commands. I can talk about it later if you want. I have a quick demo of the software, but I don't know if I have time. But we can please come and show the installation. And as I said, the installation, we made a new visualization that is outside of the software, but please come and see it. Thank you very much.
Thank you. So this ends this session.
Thank you, Frederic. Short couple of announcements. The first one is related to security. So as you saw when entering the conference, we now have a security guards in front of the conference entrance. So please never forget to take your ISMIR badge with you, because if you don't have your ISMIR badge, there is no way you will be able to enter the conference now. So it's for security reason, and I just recommend you to do as I do now, to always bring my laptop on the back of me. It's not really convenient, but we really want to have no laptop stolen today. We will have a very busy day, so we start with the unconference, with the presentation of the interactive machine learning music for music installation. We will now move, as yesterday, to session C. This afternoon, we will have session D. Today, during lunch, we will have the cocktail, the ISMIR cocktail, Women in MIR, which is really important in our community. Then we will have the ISMIR session. And this evening, we will move back to Telecom Paris as for the tutorials on Sunday. And we will have the unconference. So there is, on the website, on the ISMIR 2018 website, there is the link on the pad on which you can contribute subject for this unconference evening, which I hope will be very nice. I now let the floor to my colleague Eric Humphrey, which is the chair of the session C.
Thank you, Geoffroy. Okay. I haven't had enough coffee yet. Welcome to the first session of the second day of the scientific program of ISMIR 2018. Now we're going to have a session on source separation, symbolic, and emotion processing. We are starting. Okay. First up this morning, we are going to have Sunghoon Park presenting music source separation using stacked hourglass networks.
Good morning. My name is Sunghoon Park from Seoul National University, Korea, and I will present our paper, Music Source Separation Using Stacked Hourglass Networks. As in the title, we take the problem of music source separation using convolutional neural network architecture called Stacked Hourglass Network. So let's see how it works. So unlike most researchers attending here, my major research field is computer vision, and stacked hourglass network is originally proposed to solve the problem of human pose estimation in RGB images. We apply this CNN architecture to the music source separation task. So the network structure is similar to UNet. A single hourglass module consists of a series of downsampling steps, which is followed by upsampling steps. This varying resolution structures enables the network to learn both features from holistic images and features from the details at the same time. The major differences with UNet is that there are convolutional layers in the skip connections, and features from the same resolution are connected as a summation operation, which makes the network to learn residual features. Also in this paper, multiple hourglass modules are stacked together to refine the results of previous modules. Here's the overall framework of our source separation system. Input is the spectrogram of the mixed source, and the network outputs estimated masks for each source. The masks are multiplied with the input spectrogram to generate spectrograms for each source, and the estimated spectrograms are compared to the grounded truth to minimize the loss functions. So in this paper, we separated 2 or more sources in a single network. Therefore, number of output channels is the same as the number of sources to separate, and each channel generates a mask of each source. So loss function is defined as the sum of the absolute values of the differences between grounded truth spectrogram and the element-wise multiplication of input spectrogram and the estimated mask. The loss of the whole network is the sum of the losses of all stacked hourglass modules. So our framework showed good performance on the singing voice separation task. In the MIR1K dataset, our method is superior to others with a large margin, and you can also see that the results get better when more hourglass modules are stacked. And we also tried the multi-source separation task using a single network. Here, the performance is measured in median SDR value, and our method is actually inferior to the state-of-the-art, but showed a reasonable performance. And as there are more sources to separate, it gets harder to learn the multiple separating masks in a single network. And here we show quantitative results. Qualitative results. So this network is trained on DST 100 dataset and fine-tuned on each singer. So sample codes for our work is publicly available on the GitHub, and you can listen to more sample results in the poster session. So I would be happy to discuss about the details of my work at the poster session. Thank you.
Okay, first an announcement. If you are presenting in any of the oral sessions, please find your paper numbered chair at the beginning of the session. We're using that for queuing. Next up we have Rainier Duval, who will be presenting deep neural networks with voice entry estimation heuristics for voice separation in symbolic music representations.
Okay, sorry for the small delay. So, in the domain of symbolic music representation, voice separation is defined as the task of separating a musical work into independent constituent voices. A voice separation, especially in polyphonic music for more than 3 voices, is a difficult task, even for professional musicians, and it's an open MIR problem. It is, however, a very important task, as it is a necessary step for several other open MIR problems, such as automatic transcription or pattern recognition. Existing models for voice separation can be divided into a variety of rule-based and machine learning models, but as to now, no deep learning models have been used for the task. So the main contributions of our paper are the implementation and evaluation of deep neural networks for voice separation, the implementation and evaluation of improved voice entry estimation heuristics, I'll explain that in a bit, and the creation of a public benchmark data set for voice separation, which up to now also does not exist. So we formulate the problem as a multi-class classification problem where we assign individual nodes to one of V voices, the classes. And for this task, up to now we use a pretty standard deep neural network with an output layer of size 5, where each neuron represents one of the classes. And we integrate this model into our framework for preprocessing, feature extraction, and cross-validated training and evaluation. We evaluate the model on our curated MIDI data set that contains 78 keyboard works by Bach, Fuchs, and Inventions. And this data set is made publicly available at the link. We use 4 metrics for evaluation, and we use 2 different modes. The first one is test mode, where we calculate the feature vectors using the correct voice labels, and application mode, where we calculate them using the model-generated voice labels. So this would be the real-world situation where you apply the model to unseen data. Now, the problem is that in application mode, model performance is hindered by error propagation. And this effect is particularly strong in openings of pieces where the number of voices may not be full. So if you, for example, take this example, suppose that this first note, the C, is assigned to the wrong voice, let's say the bass, then it's very likely that the model will decide to assign each following note up until to the first chord to the same wrong voice. So, wrong direction. To tackle this, we apply a preprocessing step that applies a voice entry estimation heuristics, H1 and H2. And these estimate which notes belong to the new voices at each density increase. So, wrong direction again. So each new voice at each density increase is indicated by the blue notes here. So you see a voice enter, the first voice enter density 1, second voice enters density 2, and so on. Now, H1 is the more generic heuristic, and this determines the lowest cost configuration or connection of density increases, while H2 is designed specifically for imitative music, and this finds a pattern in each density increase. These heuristics share a similar overall algorithmic structure. However, H2 is only called if the voices enter successively, so if the music is imitative, and if not, H1 is called. We performed 3 experiments. Experiment 1 is a hyperparameter optimization experiment. Experiment 2 investigates the effect of using deep neural nets and integrating heuristics. And experiment 3 compares our best model with the state of the art. Now, if we use the 2-layer network, which we found to be 2 hidden layer neural network, which we found to be the best model, we see that deep nets, indicated with the D, always outperform shallow nets, and that integration of the heuristics integrated with /H always outperform models without heuristics integrated. And we also see that our model performs almost as close to the best model.
Thank you, Renier. Next up, we have Ethan Menelo presenting the Northwestern University Source Separation Library.
Hi, I'm Ethan Manilow from Northwestern University, and as you can tell, I'm presenting, not yet. So, Northwestern University Source Separation Library. So as we just saw, so source separation is the process of decomposing a mixture of sounds in an auditory scene into its constituent parts, as pictorially demonstrated by this beautiful graph. And here's an example of source separation. What you're going to hear first is you're going to hear 6 seconds of the mixture, and then you're going to hear 6 seconds of an estimate from a source separation algorithm called the two-dimensional Fourier transform. If I can find the mouse here. Awesome. So what is Nuzzle? So we call this project Nuzzle, Northwestern University Source Separation Library. And so Nuzzle is an object-oriented open source Python package for audio source separation. We also think of it as a framework for prototyping and benchmarking new algorithms against old ones. And it has a lot of classic algorithms and a few state-of-the-art algorithms, as well as integration with common data sets and common evaluation metrics. Yeah. So why do we do this? So in the source separation community, the MIR community, we've standardized a lot of things. We've standardized the tasks that we do, vocal separation, the CSEC and MIREX tasks. We've standardized data sets. We have the GSD100. We have ICALA MIR1K. We standardize evaluation metrics. But there's really no standard code repository for all this stuff. And Van de Waal and et al. Would argue that the implementation is the research. So in the computational sciences, your code is actually your research. So distributing this and getting this into the hands of other researchers and other people is really of the prime importance. And we hope that Nuzzle will fill that gap. So what is actually in Nuzzle? So I'm not going to go through all these, but there's over a dozen algorithms, and we are open source, so we're hoping that you'll contribute yours. And we have data set hooks and evaluation metrics. One thing I do want to point out is that we do have, because we're in the era of deep learning now, we do have the ability to host and distribute your trained models if you want to contribute that. So here's a quick code example. I'm not going to go through everything, but this is 2 algorithms running on the entirety of the MIR1K dataset, and it's 22 lines of code, including comments and stuff like that. So I think it's pretty easy to use and pretty cool, but I'm biased. So we did a few example experiments with this in our paper. One of them I'm going to highlight is this cascading algorithms, where we extended work by Zafar Rafi, and we used the API, and we were able to mix and match 4 by 4 combinations of algorithms in 2 ways. So we ran like 32 algorithms in total with like 150 lines of code. And yeah, come check us out at our poster session. Here's all of our GitHub and demo and the documentation links. And if you want to contribute, come talk to us. Thank you so much.
Now, we will have Meinrad Mueller presenting on behalf of Jacob Abser, improving base saliency estimation using transfer learning and label propagation.
Hello. This work deals with improving base saliency estimation using label propagation and transfer learning. So the first main author is Jacob Abser, who just became father for the 2nd time, so he couldn't make it to the conference. The second main author is Stefan Balke. He has finished his PhD and moved out of my lab. My name is Meinrad Müller, and it is my great pleasure to present this work on behalf of Jakob and Stefan. So what is a walking baseline? So it's not the trumpet, it's what you hear in the background. It's the regular quarter note movement, typically played by double bass, which is very characteristic for a piece of music. In this contribution, we consider the task of extracting the bass frequencies from polyphonic music recordings. And the challenges are that the bass is often not prominent, as you just have heard, and that the training data is rare. Okay, in our experiments, we use a kind of standard deep learning approach. The input is a constant Q transform, the output is a base salience representation of a similar format, and then we just use a fully connected deep neural network consisting of 3 to 6 hidden layers. That's the basis for our experiments. And as you know, training data is rare, and we need lots of that for deep learning approaches. So we make 2 contributions in our experiments. First of all, we use label propagation to start with an unlabeled frame. Then we do a kind of nearest neighborhood search to identify the best match within the labeled frames. Then we just take the label of the best match and attach it to the unlabeled frame and extend the data set accordingly. That's the first thing. And the second thing is that we use transfer learning, where we pre-train a network on a general data set. In this case, the general data set consists of isolated nodes, samples that are taken from a sampling library, so data that is easily obtained and annotated. And then we retrain the network on a task-specific data set. In our case, it's ensemble recordings where we only have few labeled frames, so to say. And as for our experiments and results, please come to our poster. Thank you.
Thank you, Meinrad. Now we have Carl Sothal presenting improving peak picking using multiple time-step loss functions.
Hi, I'm Carl Southall, and today I'm presenting improving peak picking using multiple time-step loss functions, which is work I did with Ryan Stables and Jason Hockman at Birmingham City University in the UK. So the output of deep learning systems utilized for frame-wise binary classification tasks is known as an activation function, and this basically represents a particular feature over time. For example, in onset detection, frames that contain an onset are labeled as 1, and frames that do not contain an onset are labeled as 0. Now, in reality, these activation functions aren't created perfect, and so you still need to perform class determination. For example, does the point at time step t correspond to the 0 class or the 1 class? Now, simply using rounding to do this has proven to be ineffective. For example, this point should be in the 1 class, but it's actually determined to be in the 0 class. So the majority of existing state-of-the-art systems, for example, in onset detection and automatic drum transcription, utilize what is known as peak picking. And this usually consists of a threshold and then identifying local maxima. So the loss functions actually used to train these systems is not compatible with peak picking. For example, cross-entropy compares the amplitudes of just the single frame t, whereas to actually understand a peak, you need to look at both the amplitudes, but also the relative difference between sequential frames. So to overcome this incompatibility, we propose a new loss function termed peakiness cross-entropy, which consists of cross-entropy and a new peak salient measure. So we experimented with 2 peak salient measures. First, multi-individual, which combines multiple individual frames of cross-entropy to ensure that changes to the current frame do not cause bigger changes in the larger picture. And secondly, we directly compared the derivatives of the target against the output in multi-difference. So in total, we implemented 3 loss functions. First, MI, which utilizes multi-difference and cross-entropy. Then MMD, that utilizes multi-difference and mean squared error. And then WMD, which utilizes a weighted version of cross-entropy and multi-difference. So we evaluated all of the new loss functions against existing cross-entropy in 2 MI tasks, onset detection and automatic drum transcription. And in both cases, we utilized 4 deep learning systems to ensure that the results are consistent.
So the results highlight that in both cases, all of the newly proposed loss functions achieve higher F measures, precisions, and recoils than existing cross-entropy, and this is also consistent across all of the implemented systems. And the WMD loss function achieved the highest results in both cases. The onset detection mean recoil and the automatic drum transcription mean F measure and precision were all found to be significant. So after we'd found those results, we tried to understand how this improvement is actually achieved. And so here you have an example cross-entropy loss function at the top, and below that you have an example WMD loss function. And as you can see in the cross-entropy loss function, there are two false positives, which are not present in the WMD activation function. So that basically the WMD activation function gives these points a large error, so they are squashed. Now, the consequence of this is that the true positive in WMD is also lower. However, it's still clearly a peak, so is chosen. The code is available on my GitHub, and this will also soon be incorporated into my automatic drum transcription open source software. Thanks for listening, and please come and see the poster.
Next up, we have Jan Schluter presenting zero mean convolutions for level invariant singing voice detection.
Okay. Good morning, ISMIR. Hello, Timeless Internet. So Bernard and me looked at singing voice detection using a state-of-the-art convolution neural network, and we found something curious. I'll show you an example. Have a listen and raise your hand if you hear singing voice. So nobody heard singing voice. We'll ask the neural network. Great, no singing voice throughout the excerpt. Now we'll just turn up the volume a little bit. Raise your hand if you hear singing voice. So still no singing voice, right? We'll ask the network again. Ta-da, singing voice. We can also make it a little bit quieter, and then the predictions become a little bit lower. So it seems the predictions of the network are somewhat correlated to the magnitude of the input. Yeah, and why is that? It turns out it's already in the data. Typical data sets for this task exclusively consist of tracks that contain singing voice. And in these tracks, singing voice is the most important instrument, so producers make sure it's very easy to hear. And a classifier will, of course, also pick up this cue. In fact, you can just put a threshold in the input magnitude, on the spectral magnitude, and you will get a better than random singing voice detector. Now, we fix this by just adding a lot of instrumental tracks to the data set. So in these tracks, there's some other prominent instrument, so the correlation disappears. And we can train a neural network on this new data set and see how it does on another example. Again, raise your hand if you hear singing voice. Okay, we can ask the neural network again. No singing voice. And we can make it a little bit louder. Still no singing voice. Great, so it works. We can also make it a little bit smaller and, oh. So maybe it has turned around now. Let's try another example. Raise your hand if you hear singing voice. Okay, so now everyone heard singing voice. We'll ask the neural network, singing voice. We can make it a little bit louder, and it's gone. We can make it a little bit more louder. Oh, I'm always on the wrong slide. And it's quieter, and it's also gone. So, we could now try to figure out what exactly is going wrong here, which would also be very interesting, but instead we figured we don't want this. We want level invariant singing voice detection. Okay, so In other words, we don't want the classification error to increase when we change the scale of the input signal. And we tried 4 different methods for this. One of them didn't help. The others are level invariant, but they also result in well, slightly worse classification error. And then we invented a 5th one. It works better than all the others, and it's based on a very simple idea. We use a convolution neural network with logarithmic magnitude inputs, and we constrain the convolution kernels in the first layer to sum up to 0, so they can only compute differences. This removes any information on the input scale. So this is the full title of the poster. Come to our poster if you want to discuss on horses and on other applications of this. Thanks.
Okay, next up we have Matthew Andrew, who will be presenting music generation and transformation with moment matching scattering inverse networks.
Hello everyone, I'm Mathieu and I'm going to present you a joint work with my PhD advisor Stefan Mala on music generation with scattering inverse networks. So the goal of this work is to open the black box of deep generative models. Very modest. Recently there has been a lot of high quality music synthesis results with deep models, for instance the WaveNet. And these models have very good quality, but we don't understand them. They have a complicated architecture which we can't really understand in terms of signal processing. So what we would like to do here is to simplify this network in order to identify the main structures which enable these results. However, we might slightly lose in quality, but what we would like to do is to preserve the main features, the main properties of this network. To do so, we're going to use a standard autoencoder approach where we take a musical signal X as an input, which is mapped through an encoder, which is a CNN, to a Gaussian noise vector. And then a generator maps back this latent code to this signal. Then, when we sample a new white noise vector, we can generate new signals through the generator. Usually, both networks are trained jointly. Here, we decide to predefine the CNN encoder using priors. In turn, the generator will be simply trained to solve an inverse problem, which is much simpler. In order to define our encoder, we'll use priors on the signal. We'll exploit that they are sparse in time-frequency domain, that they are stable to time-frequency warping. We'll also make sure that the encoder preserves the information on the signal in order to be invertible. And we'll use the fact that it's possible to generate Gaussian signals simply by averaging, thanks to the central limit theorem. This leads us to define the encoder as a wavelet scattering network, which is a predefined CNN, which works as follows. It first makes a wavelet modulus transform, then performs a 2D filtering of this log spectrogram, which results in a very large tensor. And this tensor is then time averaged, subsampled, and whitened, which leads to the encoder. Then the generator is a very standard architecture, which has first a linear RNN layer, a cascade of causal convolution followed by upsamplings, which results in a new signal X. It's quite close to what is used in standard deep networks, for instance, the parallel wavenet, but we are able to explain the temporal structure because we know the encoder. Also, we train it with an adapted new metric. So let me show you an example of music synthesis that we can do with white noise. The network was originally trained on piano music. We are also able to not only generate new signals, but we're also able to transform these signals just as VIEs are able to manipulate signals in the latent space. In this case, we're able to perform pitch transformation. So here is an example. Right, so to conclude, we've introduced a simplified autoencoder where the encoder is predefined thanks to priors. It reproduces the main features of deep noise, notably synthesis and transformation of music signals. The poster will be at C7 just over here. I'll be glad to discuss all the details of this paper with you. Thank you very much for your attention.
Next, we have Daniel Stoller, who will be presenting Wave UNet, a multi-scale neural network for end-to-end audio source separation.
Okay, the Wave unit is joint work by me and Sebastian Evert and Simon Dixon. The motivation is to do audio source separation. So for example, you can have singing voice separation, which tries to separate the singing voice from other instruments in the music piece. Applications include karaoke generation or lyrics transcription and many more things. Previous work has been almost exclusively based on spectrogram representations, meaning we take the mixture audio signal and convert it to a spectrogram. Then that spectrogram gets fed into a separation model, which then outputs a source spectrogram estimate. As a last step, we need to convert the spectrogram to an audio signal. And this is the problematic step, since we don't have a matching phase and we need to reconstruct it approximately, which tends to result in output artifacts. So recently, there have been a very few time domain approaches specifically for separation, but that can avoid this issue. But here you encounter another problem, which is that you have very long-term dependencies in raw audio signals. So for example, 2 seconds could already mean 90,000 time steps, so you need to model these dependencies across very long distances. And as a result, the models so far have been either very context deprived, meaning they only operate on very small chunks of audio, or just quite slow because they're recurrent and they only digest each small input chunk at a time sequentially. So we wanted something better. And our solution to that is the Wave unit. It is inspired, obviously, by the unit, as you can see in its name, and also by wavelet multi-rate analysis. The core idea is here, to compute a feature hierarchy, meaning we compute features at different timescales by repeatedly convolving over the current features and downsampling them. And this allows us to efficiently do long-term dependency modeling, since we can use the features on the coarser timescales. It's a very simple system to implement, since we also don't need any input or output pre or post processing. We also make further additional contributions aimed at reducing artifacts in the output. So the results are that we can show an improvement in performance over the spectrogram-based equivalent, which is the UNet proposed by Janssen et al. We also participate in the SciSec separation challenge, where we achieved an encouraging performance. And some of the additional adaptations we make are able to bring further improvements to the separation results. The code, the trained model, and also audio examples are available in this GitHub repository, so like and subscribe. And finally, some audio separation results. So you can hear a mixture signal first. And now you can hear the vocal separation result from our model.
Hear you call my name, I know I must read.
So as you might hear, the typical artifacts that are created during the spectrogram reconstruction stage, which result in kind of wheezing sounds and sinusoidal residual signals, are attenuated greatly. Yeah, thanks for your attention.
Next, we have Claire Savard and Aaron H. Ugby presenting SE and SNL diagrams, flexible data structures for MIR.
I'm Erin, and this is Claire, and today we will be discussing research conducted at ISMIR in Providence, Rhode Island. We introduced 2 new data structures for addressing the cover song task.
So this research builds off of previous work that was done by Kinnaird back in 2016, where she took information from the self-dissimilarity matrix, took out those repetitive structures, and placed them on the same time axes. And so what we're looking at in our aligned hierarchies are all possible repetitions that occur in this song. From there, we were inspired by topological data analysis to look at features in our data set. So we took our start and our length of each of these repetitive structures and put them on a start normalized length diagram, which we see on the rightmost structure. So one of the biggest things about this start normalized length diagram, or SNL, is that we are emphasizing the length of these repetitive structures versus their start time. And so what we actually do with the start is we normalize it based on the length of this entire song. So instead of looking at, say, a repetitive structure that starts at beat 50, we take a look at where proportionally it occurs in this song. So say in the middle of the song or 3/4 of the way in. This allows us to avoid any type of resampling by putting all of our songs within these same limits, 0 to alpha. In this case, we're seeing 0 to 1. And preserving this length component of each of the structures so we contain that information. We also can use many pre-existing metrics from topological data analysis, which can compute a distance based on these start normalized length diagrams, which correspond to the dissimilarity between these songs. These metrics already have a lot of pre-existing theory to them, so it's really nice we could just kind of adapt it to this method. Based on what we've been seeing thus far with these SNL diagrams, we have a lot of comparable results to what we've been seeing previously in Kinnaird's method with these aligned hierarchies. But we actually have a more complete data set because with these aligned hierarchies, we can only compare songs that are the same exact length. However, here, since we've normalized this start component, we are able to compare any songs that have any repetitive structures in them and that we can convert into our start normalized length diagram.
And here are the results from 10 experiments using kern files from the CHARM project. Our data set consists of mazurka scores by Chopin, and for each of these scores, we have 2 versions. The first version contains all of the repeated structures, or all of the repeated parts of the song observed as intended by Chopin, and the other version ignores these repeat markers. And in the cover song task, we aim to match these 2 songs together. And the results are competitive, we are seeing, and these are shown here. And we look forward to future work going through pre-processed audio data and extending these SNL diagrams to be suitable for more machine learning tasks. Please come to our poster at C9 if you would like to hear more about both the SE and the SNL diagrams. Thank you.
Next, we have Corey McKay, who'll be presenting JSymbolic 2.2, extracting features from symbolic music for use in musicological and MIR research.
Right, so symbolically encoded music plays an essential role in a number of important fields. You see this in musicology and music theory and the library sciences. And what's great in these fields is there's more and more work being done using computational methods on really large data sets. And that fits really nicely with what we do here in the MIR community, where we have a lot of techniques and approaches that could be adapted to these fields. But unfortunately, although we've done a lot of work in audio and other fields, there's not as much software and not as much research that we've produced that can be used in these domains. So in this context, I'm presenting the JSymbolic software, which extracts features from symbolic music and is part of the larger JMIR software suite. So once you've extracted the features, you can use them for a variety of things. You can do machine learning with them, you can do statistical analysis, and you can also do content-based retrieval. So the current version of the software extracts a total of 246 unique features. And if you expand the multidimensional features in there, you end up with almost 1,500 separate variables values for each symbolic file that you extract features from. So these features look at information like pitch statistics, melodic intervals, chords, vertical intervals, texture, rhythm, instrumentation, and dynamics. Part of the goal of the software is not only to provide sort of a out-of-the-box feature extraction suite, but also to provide a framework that you can use to extract or to design your own features that researchers can use for their own particular needs. So with this in mind, there's a modular plugin interface for features, and there's also built-in testing and debugging modules in the software as well. And in particular, it's easy to build new, more sophisticated features based on the values of existing features. There's 4 different ways of using JSymbolic. There's the GUI for ease of use, there's a command line interface, there's an API for those who want to incorporate JSymbolic into their own software, and there's also a Rodin workflow for distributed computing. We also put a particular emphasis on usability. So the code is very well documented, but there's also quite an extensive manual that comes with the software, and there's also a tutorial that includes worked examples. There's a few miscellaneous aspects too that I want to highlight as well. First of all, you can do windowed extraction as well as overall extraction from symbolic files, which of course is very common in audio, but less common with symbolic music. You can also save configuration files for individual jobs, which can be great not only for keeping a record of what you've done in different studies, but also for purposes of repeatability of research. We have a secure feature subset, which is useful if you're dealing with biased data sets, so these features are particularly safe and less susceptible to some of those problems. You've got a tool for detecting those kinds of biases in data sets so that you know that they're there and you know to use the safer features. And you can also use JSymbolic with the other JMIR components if you want to do multimodal research involving matched audio files or lyrical data or cultural data. So we've done a number of experiments on JSymbolic to validate its performance, and we got pretty good results both with respect to genre classification and composer attribution. But what's particularly interesting is not just that we're able to distinguish between different genres and composers, but we're also able to get musicologically meaningful insights using the features. So for example, in our composer attribution experiments, we're able to test a number of sort of predicted results based on scholarly expertise, and we're able to see that actually 3 of them were correct and 6 of them were incorrect, which is an interesting result. And we're also able to use statistical analysis of the features to see differences between compositional styles that weren't actually published in the literature already. So thanks very much.
Next, we have Louis Spiegel, who will be presenting relevance of musical features for cadence detection.
So, hi everyone. Let's begin this presentation by listening to musical extracts of a string quartet written by Joseph Haydn. Okay. So you might have perceived a stronger closure feeling despite it's not the end of the musical piece. This closure is due to the end of a musical sentence, and in music it's what we call a cadence. So we have musicologists have identified markers to help us identify cadence, and for example, it's a bass. In the bass, you have the voice leading move, a descending fifth, and it can also be an ascending fourth. We also have the leading tone going to the first scale degree pitch here on the first violin. We also can look at rhythmic markers. Here we have a rest after the arrival point of the cadence. We also look for preparation chord. So here we have the second scale degree chord before the dominant chord. We also look at other markers. So here we look if we have all the pitch of the scale on the recent past of the cadence. So once we have all these markers that we consider as features, we can extract them on a corpus constituted by a string quartet written by Joseph Haydn and fugues written by Bach. Here, as a result of the extraction, I will focus on the first feature I presented you. It's the fifth, the descending fifth on the bass. Here you can look that it is activated for a little less than 1 out of 10 bits. But it is also activated for almost all cadential bits. That's why we can say that this feature is significant. It was expected. So with this extraction, we can now detect cadence. So we cut our corpus into halves. The first half is our training set, where we train a support vector machine. And the second half, we try to solve the classification problem. So as you can see in this chart, we have fairly good results with Haydn quartets. We detect over 80% of perfect cadence on this corpus. We also try to detect half cadence, but with less success. So thank you for your attention, and come to see our poster.
Zhao Hu will now be presenting on the relationships between music-induced emotion and physiological signals.
Good morning, everyone. I'm Xiao Hu from University of Hong Kong. On behalf of the second author, I pressed it too much. Okay. On behalf of the second author, Fanjie Li, I would like to thank the Women in MIR initiative because Fanjie was supported by the initiative to attend ISMIR last year. And she was an undergraduate in Sichuan University in China, but now she's a master's student in University of Hong Kong under my supervision. So thank you very much, ISMIR. Today we are going to talk about using a wearable device to measure physiological signals of the human beings and to detect their emotional response to music. Why wearable device? It's because there are lots of advantages of this kind of methods to measure physiological signals. They are objective, they are unobtrusive, and they can measure the signals in real time. And potentially, this can be used in naturalistic settings to study users' reactions to music. So in this study, we try to find out the relationships of emotion and those physiological signals. And also, we'd like to see if there are individual differences in such relationship. This is what we did. We made a user experiment where users can interact freely with MIR system. It's called Moody, which can support searching for music by emotion and by genre, etc. The only difference is after listening to one piece of songs, the user needs to answer some questions regarding to their emotions at that moment. So we emphasize that it's the induced emotion after listening to the songs. It's their emotion, it's not the song's emotion. So they need to choose those emoticons. So that was very interesting. And then at the same time, we measured their physiological data using a wristband showing there. It's called Empatica E4, which is quite high-end and has been used in many studies in psychology and social sciences and health science-related topics. So in this experiment, we had 23 participants, and they listened to over 600 songs. And we particularly measured those signals regarding to electrodermal activities, which measures the sweating condition of the skins, and also the blood volume pulse and heart rate, which derive the interbeat interval, and also the skin temperatures. So with those signals, we did data analysis. We extracted those so-called indicators from the signals, which include the statistical-based indicators and time series based indicators, frequency domain ones, and also physiological signal-specific ones. With all these indicators, we did statistical tests to see whether those indicators can tell the different emotions, particularly negative or positive emotions in the mood dimension and in the arousal dimension. And then we made a classification experiment to see whether those signals can tell us. Okay, this is the last slide. The result, in short, some of the signals actually worked in detecting emotion. And individual differences are very prominent. So for details, you can come to our poster and I can explain to you in more details. And there are lots of future work. I hope that you can join this kind of topic and we can work together. Yeah. Thank you very much.
Roman Enequin will be presenting music mood detection based on audio and lyrics with deep neural networks.
So good morning. I will present you our work about music mood detection from both audio and lyrics. So this is actually the work of the master's thesis of Rémi Delhuis, who unfortunately couldn't be here today. So thanks to him for letting me hold the work of this presentation. So where do I switch the stuff? Here? Okay. Does it work? Okay, sorry. So if you have tracks with audio and lyrics and you want to do some mood detection, for instance, a very simple binary happy sad classification task, you can design a system based on audio only that will provide you the probability for a track of being happy, which is given on the x-axis here of this plot. And you can design another one based on lyrics only, that will also provide the probability of being happy, given here on the y-axis. And then if you plot both this probability in this plot, for every track you got that kind of figure where blue points are happy tracks and yellow points are tracks that are annotated as sad. So if you then take a decision based on only the probability predicted by the audio, you will have this vertical bar, and you predict everything which is on the right as happy and on the other side as sad. If you take your decision on lyrics only, you will have this horizontal decision threshold. And so for both, we have a better than random accuracy, so they both bring some kind of information, but obviously what you want to take is the top right points. So basically you want to have this diagonal decision. So what we just saw here is that both audio and lyrics carry information about mood, and that some very basic light fusion improves the result of our monogonal. So they both carry complementary information. So this is not a new result, but actually not much work has been done on the subject with deep learning or smarter fusion, and that's what we've done. So basically, we do audio plus lyrics mood detection that we formalize as a regression problem in the valence of result space. So we use audio as mail spectrogram and lyrics as word embedding sequence. And guess what? We are using neural networks for both audio and lyrics with several architectures that we compare. We also design a data set with semi-automated annotation in the valence arousal space. And so what is the contribution of our work is mainly comparing between deep learning models and a standard, more classical approach, which is a kind of state-of-the-art for this task. And we also compare different, we compare fusion with unimodal approaches and different kind of way of merging the information. We also release the annotation of our dataset for comparison purposes. Oh, this is very stressful. So let's conclude. So what we show is actually deep learning models are a bit better on arousal detection, but we get similar performances on valence detection. We also show that mid-level fusion is better than late fusion, and that both deep learning and classical approaches are complementary. If you merge both, you get better results. So that's all. Come and see your poster. Thank you.
Now, Emilia Parada-Caballero will be presenting Identifying Emotions in Opera Singing, Implications of Adverse Acoustic Conditions.
Hi all, so I'm Emilia, and I'm going to speak about the identification of emotions in singing voice. So in this recording, there was some background noise. We could not listen so much because it was not so high the volume. But this is typical of analogic recordings and mostly of live performance. So what we want to do in our work is to evaluate how this noise might influence our perception of emotion in voice. In this case, we are going to apply methodology typical of speech-emotion recognition in perception, which actually deal more often with noise than what music used to do. And for this, the first step is to choose a data set. We're going to consider a cappella opera singing. So we have a nonsense musical instance to don't bias the listeners by the linguistic content. And different singers are going to perform these utterance in different emotional states. So to understand better, I'm going to show some examples. The first is how one of the singers expressed the emotion hot anger by pronouncing this utterance. Okay, now the same singer, same utterance, but depressed sadness. And finally, elated happiness. So one time we choose the utterance, we are going to noisify them by applying 3 noises, white, pink, and brown, by considering 4 signal-to-noise ratios. Then we made a perception test. We considered 132 listeners who evaluate the utterances, both clean and noise, through our cross-sourcing platform, I Hear You Play. The result shows that male singers are perceived a bit more accurately, and that listeners, female listeners, are more accurate than males. The difference is not big, it's not statistically significant, but in any case, it's consistent. Always females perceive better. This is not by chance, happen also often in the perception of emotions in speech. Then the difference between noises is almost none, so we will say that noise effect, as stronger the noise, lower the accuracy of the perception, but in any case, there is no one noise effect more than another one. Then we apply some machine learning, nothing fancy, nothing new. We want just to see how the machine performs against the human, so to compare machine learning to perception. For this, we made binary classifications. We used a perfector machine with linear kernel, optimize the complexity of the development set. We divide the singers in different folds, so to perform a singer-independent task, different singers are for training, development, and test. And we made the classification by considering compare feature set, and also the subset of this. So also we made experiments by considering MFCC, spectral, prosodic, and voice quality features. The results show, as in perception, that the noises somehow influence the same, and that MFCC perform much better, voice quality worse. This is different than what happened in speech, because in speech, voice quality features perform also quite well. In this case, the reason is that we had opera singing, and for this, the voice is projected, so the difference between emotions is going to be minimized. That's all from my side, so thank you so much for your attention.
Now Renato Panda will be presenting musical texture and expressivity features for music emotion recognition.
Hi everyone, my name is Renato Panda, and this work is about musical texture and expressivity in music emotional recognition. So, in brief, we know that music is kind of a language of emotion, and as a result, over the last 3 decades, we have assisted to several works, from symbolic formats to audio signal, using classification, using regression, and a myriad of other solutions over the last decade. Still, several problems are open. Some of which are the glass ceiling, as in the results have been stagnant over the last years. We also have some known issues with the data sets. And finally, there is the semantic gap, as we need more and additional features that are emotional relevant and that may help reduce the gap that exists between the low-level signal and the high-level concepts that we as humans associate with emotions. We believe that most of the efforts have been devoted to machine learning, data sets, and although new solutions such as deep learning will surely help to improve the situation, their decisions are also hard to understand, as in it is hard to extract knowledge from it. And with this in mind, in our work, we start with a broad review. First, on the musical field, we review the elements of music, organize them in 8 classes, such as rhythm, dynamics. We passed on to emotion. We try to understand how these concepts relate with specific and are associated with specific emotional responses. And then we went back to the other features that exist in known frameworks, and also tried as much as possible to organize them and to relate them with these 8 concepts. So what did we conclude? We noticed that first, these audio descriptors are highly unbalanced across these 8 classes. And also there are some classes that, some musical concepts that are said to be relevant emotionally, but they lack other descriptors that might capture this information. So, with this in mind, we built on previous work by Salomon and Emilia Gomez, by Dressler. We also adapt some of our work, some of our previous work, and propose a set of descriptors that are related with musical texture, with articulation, glissandi, vibrato, and others, that although not being quite complex, from our experiments, proved to be efficient and to help improving the results. We also achieved some interesting insights about emotions and music and their relations. So if you are interested, please come and ask. That's it. Thank you.
Now we have Andre Offner presenting shared generative representations of audio concepts and EEG to reconstruct perceived and imagined music.
All right.
right. Hello, everyone. I'm going to talk about a shared generative representation of audio and EEG in order to reconstruct perceived and imagined music. So a quick overview about the two basic questions for this research. So the first question is, can we find a way to reconstruct perceived and then maybe even imagined music from electroencephalography data, which is the electrical signal that the brain emits through the skull? And the second question is, can we learn and describe concepts that are shared in audio and the brain signal? And ideally, we could do this at the same time. So here you can see the basic experimental setup. So subjects sit in an audio booth and listen to music and are asked to first listen and then imagine the music. At the same time, the EEG signal is recorded, normally into 64 channels or 128 channels. So from this EEG signal, and maybe also using the audio signal as training targets, we now want to reconstruct the audio. Here we tried to reach Mel spectrogram reconstructions, and at the same time we also try to link those Mel spectrogram reconstructions to the brain states that they correspond to. So how did we tackle this problem? We used a combination of canonical correlation analysis, which normally is deterministic, but here we used a probabilistic version of it in a combination with a variational autoencoder, which uses deep convolutional neural networks to process EEG data from more or several subjects and compresses EEG data into a shared latent representation, which we then use to simultaneously reconstruct the EEG signal back, so like in the traditional autoencoder, but also reconstruct the mass spectrograms of the audio signal and some auxiliary classification tasks, like, for example, the loudness or the trial condition from the same latent representation. So we used two data sets for this. One data set which featured both perception and imagination of quite simple looped speech and corresponding sine wave patterns, and a more complex and a large data set which featured full-length pop songs, so naturalistic music. So here you can see some of the very typical results we got. So for both data sets, we got results that look musically meaningful. On the top right, you can see some reconstructions for the looped speech and looped sine wave patterns. So we got reconstruction that look meaningful from a temporal, rhythmical, timbral, and loudness perspective. And furthermore, we also got pretty good-looking results for the naturalistic music. However, here the rhythmical and temporal aspects really were dominated by the timbral aspect. So now here we see that within this latent space, we could learn some concepts. Here's an example for interpolating between a rhythmical trial into a speech trial. And for this interpolation between real stimuli, we also get the corresponding brain patterns. So we hope that this is maybe a first basis for more complex models using this approach. And I'd be happy to see you at the poster if you have questions. Thank you.
And now we'll conclude our first session of the day with Diego Furtado Silva, who'll be presenting Exploring Musical Relations Using Association Rule Networks.
Well, good morning, everyone. I'm presenting this paper by some very cool people, plus myself. I'm Diego. And we used some descriptive machine learning for exploratory data analysis on music. Actually, we used the XARN, that is the Extended Association Rule Networks. I have this toy example here. It means that if your music, if your song, have that pattern number 10 right there, it's an MFCC, we obtain these patterns using clustering-based quantization. Okay, it means that in that data set, we have 100% of confidence that this song is a classical music, right? So we constructed this kind of networks with rules from patterns to labels. It doesn't need to be genre. I'll show some more. On this side, we have some AND rules. So if you have the pattern in 23 and the 4, so you have the confidence that, not 94% of confidence that your song is classical, okay? These networks are not only for one genre, one target, but also for discovering some links between different labels. For instance, this is the network I got from GTZ dataset. So we have all the genres there and several different patterns, and some patterns are linked to different genres. It's hard to see here, but I have the demonstration. You can see in my poster. We used MFCCs there, but we also used Chroma. And I noticed that you can use any kind of features, deep learning features, or anything you want. This is interesting. We used Chroma features in the Artist 20 dataset. We found some links between Metallica, Tori Amos, and Roxette. That's weird, but it happened. We also use it to other kind of labels like energy in the Free Music Archive dataset. We found links using Chroma, and we found links using MFCC, that is more timbral stuff. It's very cool to play with that. We have a visualization tool, and I spent a lot of hours listening to the patterns and looking what those links mean. And that's why I don't have a paper to ICAST, probably. And that's it. I'm showing you some patterns. You can't look at the patterns and say, OK, that's great. But you can listen to the patterns, and I have some excerpts to show you in my poster right there. So see you. Thank you.
All right, thank you for your attention. Let's give one more round of applause for all of our excellent and timely presentations of the morning.
Okay, we are a bit ahead of time because the speakers are so good so that they keep exactly the timing. Is that the margin we prepared for the delay, so we are a bit ahead of time. So I will try to fill 1/4, speaking very slowly. No, I'm kidding. Actually, since the coffee is always there and there is 24 hours coffee, you can go for the coffee break and after go for the post session. Short couple of announcements. So this afternoon, we've got the ISMIR session, and during lunch, we will have a special cocktail offered by ISMIR and ISMIR sponsor. And there will be special games proposed by Audrey Laplante and Eva Zangerle, which are the chair of this year ISMIR event. So there will be a social networking bingo. So that means that the lunch will be a bit longer, and the ISMIR session will start at exactly 1:40 instead of 1:30. So enjoy the coffee, the posters, and the ISMIR cocktail. Oh, and as usual, for people sitting in the first 3 rows, please go to another seat or go to the coffee break, because as usual, we will have to rearrange the configuration of the room. So thank you.